additive manufacturing is one dominant area which is which are following by some of the research experts in most of the core field, that is mechanical engineers, production engineers, that they are doing these types of research. So it is a vast multidisciplinary objects. So nowadays the organ printing is one of the core area of this STDP. So here it is one question, whether it should be done by the engineers or by the doctors. So sure, the answer for this question is it should be an integral approach of both the doctors and engineers to do work together to face all the challenges. The challenges should be, for certain challenges, have the solutions by engineers, and for certain challenges have the answers one and only by the doctors. So it is an integrated methodology, and now it is still in a high peak of research and emerging research areas. So definitely this should rule our world for the hereafter for the after 10 years or 20 years. So after this, what is the necessity of our today's scenario is, in case if a patient met with an accident, or in case if a patient had any failures in their organs, so the doctors will examine their body and they will redo and check its properties which is adherence to their organs, and they have to shortlist a list of things which is required for their organs and what are the materials which is adaptable to that organs, and they have to send the list to some of the business model vendors or like that, and the business model vendors, they can get the information and they will print that organs for those specific patients, which is highly customized and which is highly customizable. And once if the organ printing has been done, they could send that organs through FedEx or Amazon couriers or etc. like that. And this is what the future is going to be moved on. So for these things, you have to know about some of the basics of tissue engineering and what are the applications of this bioprinting and biomaterials that are we are going to discuss, and absolutely what are the challenges and what are the difficulties that is going to that is facing in situ operations. That is right now in the 2021, still most of the scientists and most of the researchers are facing so many challenges in organ printing, because right now only 10 to 20% of the organ printing is still in a success rate, and the remaining 80% of the organ printing is still in the study level. So definitely in future it will be meet out and all the challenges will be rectified, and they can it will be implemented to all the patients. Okay, and last some of the successful case studies that they have done till now. This is what we are going to discuss in this next few hours. So before going to start, let us give a small introduction about the basics of additive manufacturing. So it is nothing but it is a layer by layer building of materials. So what is the purpose of this additive manufacturing is, in subtractive manufacturing, there is a quite possibility of getting wastages. So but in additive manufacturing, so here that using certain additive manufacturing additive printers, that is a 3D printers or some equipments that is related to additive manufacturing operations, that is stereolithography, SLS, SLM, lens operations. There are lots and lots of operations are there where they have built that material one and only by the layer by layer additions. So what is the advantage of it? The wastages of this particular technology is nil. So therefore you could able to get any component with zero wastages. That is one and only the advantages of this additive manufacturing. And at the same time, there are some other advantages of that. Let us discuss later. And this is the additive manufacturing process chain. So the component that we need by using this additive manufacturing would exist from the CAD model. So using that CAD model, the CAD model should be converted to an STL file. The STL file, then we can enter into some slicing softwares. That slicing software slice that entire three-dimensional objects by layer based upon the thickness of the machine parameters. Then that slice component for each and every layer should be printed by that 3D printers, and by adding layer by layer, and finally we could able to get a real three-dimensional object. This is what the additive manufacturing is going to work. And what is the main advantages of this additive manufacturing is, first one is part complexity. So while comparing to the traditional conventional manufacturing process, so part complexity, that the components which is having highly complex in structures, that is possible one and only by the use of additive manufacturing. That's why this organ printing and bioprinting is having very, very high complex parts, because in case if you want to design a cardiological vascular tissues, or in case if you want to design some intestinal tissues where it is having a very high complex in structures. So for this types of purpose, we have to prefer this types of additive manufacturing. additive manufacturing methodology. So in general, the additive manufacturing methods, which is particularly used for biological materials, that is commonly said as bioprinting. So that's why this part complexity is one of the main important thing for this additive manufacturing. The next one is mass customization. So customization is that component is quite different for each and every applications. For examples, in case if you see our fingers, so it is different for each and every person. It is one of the best example for customization. In case if you want to do a hand gloves by using this type of additive manufacturing, where high mass customization is required, because the structure, the shape, and the length and the diameters aspects and the dimensions will differ from persons to persons. So this is what it is known as mass customization. So most of the medical applications where it requires mass customization operations and instant assemblies. So using this additive manufacturing, it is possible to do some instant assembly operations. For example, in case if you are going to fabricate some wired chain operations or some interlinked chain operations, where it is possible by using this additive manufacturing operations by giving a certain clearance within these particular materials. And part consolidations. So even in case if you want to print each and every additive manufacturing components by single components, and then you are going to assemble it by using one by one. So here using this part consolidation technology, where several components can be integrated into one single component, that is possible by using this additive manufacturing. And using this additive manufacturing, it is possible to do some lightweighting operations. Now, in the upcoming sessions, we are going to discuss one and only about this bioprinting. So first, you have to know about the bioprinting. Additive manufacturing and bioprinting both are working in the same principle. But in additive manufacturing, there they have dealt the materials only with the polymers, plastics, or something metals. But in bioprinting process, even though the materials and that working principles are similar, the manufacturing process are similar, and the 3D printing machines are mostly almost similar, but here in bioprinting, that they are using only the biological acceptable materials, bio inks, and some regenerative tissues formation materials. These are all the materials which is required for bioprinting operations. And it is a very powerful tool to print complex and personalized 3D tissues with living cells and also some biologically acceptable materials. That is also possible by using this type of bioprinting. And that's why this bioprinting process is quite applicable in organ printing. So using this bioprinting operations, it is possible to create some organ-like structures with living cells. So nowadays stem cells areas is emerging. So in stem cells is integrated or blended along with certain biological acceptable materials and bio inks, it is quite possible to make the ready-made human organs. That is what the researchers are doing, the researchers frequently for nowadays. Okay. And now, just for a demonstration purpose, I'm going to show you one small video. So please watch.
There are currently hundreds of thousands of people on transplant lists waiting for critical organs like kidneys, hearts, and livers that could save their lives. Unfortunately, there aren't nearly enough donor organs available to fill that demand. What if, instead of waiting, we could create brand new, customized organs from scratch? That's the idea behind bioprinting, a branch of regenerative medicine currently under development. We're not able to print complex organs just yet, but simpler tissues, including blood vessels and tubes responsible for nutrient and waste exchange, are already in our grasp. Bioprinting is a biological cousin of 3D printing, a technique that deposits layers of material on top of each other to construct a three-dimensional object, one slice at a time. Instead of starting with metal, plastic, or ceramic, a 3D printer for organs and tissues uses bio-ink, a printable material that contains living cells. The bulk of many bio-inks are water-rich molecules called hydrogels. Mixed into those are millions of living cells, as well as various chemicals that encourage cells to communicate and grow. Some bio-inks include a single type of cell, while others combine several different kinds to produce more complex structures. Let's say you want to print a meniscus, which is a piece of cartilage in the knee that keeps the shin bone and thigh bone from grinding against each other. It's made up of cells called chondrocytes, and you'll need a healthy supply of them for your bio-ink. These cells can come from donors whose cell lines are replicated in a lab, or they might originate from a patient's own tissue to create a personalized meniscus less likely to be rejected by their body. There are several printing techniques, and the most popular is extrusion-based bioprinting. In this, bio-ink gets loaded into a printing chamber and pushed through a round nozzle attached to a print head. It emerges from a nozzle that's rarely wider than 400 microns in diameter and can produce a continuous filament roughly the thickness of a human fingernail. A computerized image or file guides the placement of the strands, either onto a flat surface or into a liquid bath that'll help hold the structure in place until it stabilizes. These printers are fast, producing the meniscus in about half an hour, one thin strand at a time. After printing, some bio-inks will stiffen immediately. Others need UV light or an additional chemical or physical process to stabilize the structure. If the printing process is successful, the cells in the synthetic tissue will begin to behave the same way cells do in real tissue, signaling to each other, exchanging nutrients, and multiplying. We can already print relatively simple structures like this meniscus. Bioprinted bladders have also been successfully implanted, and printed tissue has promoted facial nerve regeneration in rats. Researchers have created bone tissue, skin, and cartilage, as well as miniature semi-functional versions of kidneys, livers, and hearts. However, replicating the complex biochemical environment of a major organ is a steep challenge. Extrusion-based bioprinting may destroy a significant percentage of cells in the ink if the nozzle is too small, or if the printing pressure is too high. One of the most formidable challenges is how to supply oxygen and nutrients to all the cells in a full-size organ. That's why the greatest successes so far have been with structures that are flat or hollow, and why researchers are busy developing ways to incorporate blood vessels into bioprinted tissue. There's tremendous potential to use bioprinting to save lives and advance our understanding of how our organs function in the first place. And the technology opens up a dizzying array of possibilities, such as printing tissues with embedded electronics. Could we one day engineer organs that exceed current human capability, or give ourselves features like unburnable skin? How long might we extend human life by printing and replacing our organs? And exactly who and what will have access to this technology and its incredible output? For more mind-blowing medical advancements, check out this video on hacking human genes to fight cancer, or this video to see how doctors use radioactive drugs to detect diseases.
Okay, so hope you have get the overview about this bioprinting using this small short videos. And now I am telling about some of the basic operations of bioprinting. So in bioprinting, that entire operations could be segregated into three main phases. The first phase is pre-printing, and the second phase is actual bioprinting, and the last phase is post-printing. So what in additive manufacturing we can commonly call it as pre-processing, processing, and post-processing. Likewise, in bioprinting also the same categories will be done. Okay, so in pre-printing, it's mainly focused about this materials. So in bioprinting, they are focused only on this biomaterials. So there are several types of biomaterials are there, and bio inks are there, and some other materials which can be extracted from the natural natural things like natural algae or natural animal cells and live stem cells. These are all some of the biological acceptable materials. So there are some researches which could be exaggerated in tissue engineering aspects. So how to get and how to make these types of material gels, and how the biological acceptable materials can be mixed, and what are the proportions that can be taken. For all these aspects, we have to do some initial level researches in the tissue engineering. And once if the biological acceptable materials has been ready, then you have to use those materials in your bioprinters. So there are several types of bioprinters are available. So take this biological acceptable materials and feed them into your bioprinters, and that bioprinters will do this types of bioprinting as usual by this additive manufacturing operation, like layer by layer of generation of these things. But here, some nozzles have the capacity of even 400 nanometers, okay, and 400 micrometers. So even our blood vessels and vascular tissues have the capacity. There are very high customizations and high precisions is required. So for all these requirements, this bioprinting fulfills their requirements. And even though the cross-linking, what is cross-linking means, as I already said, like instant assemblies. So here using this cross assemblies, where how the actual vascular tissues and how the artillery vessels has been really looks like. And also this using this cross-linking, that oxygen supply and the blood supply and some of the nutrition supplies is also possible by using these types of complicated and complex shapes generated by using these types of bioprinting, and where it should be taken care at most high precisions and high accuracies using these types of bioprinters. And the last one is post-printing. So under the last, you have to detach those particular types of scaffolds or some biological materials that is printed. So usually most of the bioprinters has print that entire things within that immersible medium, because they need high precision or accuracy like that. And some other biological acceptable materials where they are having some soluble detections, and even in case if you add some solvents, that they have to be dissolved by using the extra support materials. And sometimes if it is needed, they have to do some mechanical test and some biological test for making these types of printing before it is implemented. And this all comes under the post-processing works. And likewise, in the pre-processing stages, where in case if you want to regenerate one particular vascular tissues or vascular one, even in case if you want to do some simple organs, where the geometry is very, very complex. For example, we cannot able to do those types of artillery tissues or even human heart or human organs by using the 3D modeling softwares, where the high medical imaging is required, because mostly the patients are veterinary objects that can be get that real organs data can be get one and only by the usage of medical imaging. So using some CT data or MRI data, where we can get that exact things components by using DICOM images. So there, in case if you go for any MRI scans or CT scans, where you can get that particular component in a format of DICOM images, so that DICOM images formats can be fed into certain computers, and they can they can be converted to point collection of points collocations objects. So where there are having several softwares are available. One of the softwares that I have known is Mimix. So it is by Materialize. Materialize Mimix is one of the softwares where the DICOM images can be converted into point cloud data. So the point cloud data can be then converted into that point. Instead of that point cloud, it will be converted to the line faceted objects. So once the line faceted objects will be then converted to the STL file, and that STL file will be re-smoothened, because it should be in some irregular shapes. There are some related time is required for making to complete this entire process by the engineers, because some smoothing operation should be there, some thresholding operation should be there. So after all these types of works, that entire STL files could be made as a smooth STL files, and it can be assembled like real human heart or human arteries, with having some complex structures with high precisions and accuracies. So this is how the CAD model has been obtained. Once the CAD model has been obtained, then that should be printed by using these types of bioprinters, by using certain suitable biological acceptable materials. So several biological acceptable materials are there. In case if you have taken the case study as particularly human livers or human kidneys, there you are having a specific biomaterials. So you have to learn and you have to do some initial research in the tissue engineering, and what are the biomaterials which is feasible for making this particular type of organs or particular types of tissues. Then take that particular types of biomaterials and do these types of bioprinting. Once the bioprinting is done, then do the post-processing. So post-processing, here it requires in several stages. You have to check it and you have to evaluate whether the oxygen supply level is correct, whether the blood circulation supply is correct, whether it can withstand the nominal temperatures regions, and whether it suits the human capacity, or whether it is biologically acceptable or not. For all these types of testing, that would be done. This is what the bioprintings are there. And there are several bioprinters are available. So using this, as I already said, So the bioprinters will just print the materials along with cells, along with some biomolecules. So these biomolecules, you have to make some tissue regenerations. So for that, it will take some exact time. So there are several ways to make this 3D bioprint. There are several ways of getting 3D bioprinting techniques. And once if it is bioprinted, so it needs certain time to make some tissue regenerations. If the tissue has been regenerated successfully, then only it is possible to make certain implementations, or else we have to go for further studies. So in case if all the biomaterials and all the bioprinting pre-processing and the post-processing testing has been the successful one, then only the tissues has been regenerated successfully, then only it is in the proper right stage to implement into certain patients or animals. And now I am going to, afterwards, I am going to discuss about some of the types of 3D bioprinters. So mostly the 4 types of bioprinters are available right now. So one is extrusion-based bioprinters, another one is inkjet-based bioprinters, then the laser-based bioprinters. The laser-based bioprinters has been segregated to 2. One is laser-induced bioprinters and another one is stereolithography bioprinters. So these are the 4 techniques that they are emerging nowadays. So let us discuss one by one. Okay. So first, this is the first one. So this is an inkjet-based printers. So first, let us discuss about the inkjet-based printers. What is inkjet printers? So here you already have taken some printouts using certain desktop printers. So the same principle is also working using this inkjet printers. So here the droplets, the ink will be in some liquids or some gel forms. So the droplets of the liquids has been formed by using some thermal operations or by using piezoelectric actuator operations. So it displays that ink layer by layer. So the same concept is available. So here, what are the limitations is that ink should be, that bio ink, it should be in low viscosity. High viscosity bio inks is not possible using these types of inkjet printers. And that bio ink must solidify after ejecting from the nozzle of this inkjet printers, it should be solidified. Or else if it is still in the liquid form, then it is not able to made adherent to the next layer, which is already happened to print, which is earlier. And this is the thing. And that bio ink, it should have certain certain cell densities, then only it just make some adherence to the one layer to the another layer, or else it will not make layer by layer generations of that certain tissues or some biomaterials. And last one is the best applications which is suitable by using these types of inkjet printers is the skin grades. So in even most of the scientists and researchers have successfully developed human skins. That is human skins which is printed by using bioprinters using this inkjet printers only. So this is what the inkjet printers are happening. So the next types of printer is laser assisted printers. So in laser assisted printers, what is the actual things happening is, so here you are having one laser source. That laser source will directly make contact with donor slides. In that donor slides only you are having some biomaterials, which is in the form of some bio inks or in some form of some gels and collagen cells. That energy absorbed layer, so the laser will pass through those types of energy absorptions using those biomaterials. That laser made that particular biomaterials and make it to dip on the other side. So that will make a formation as a layer by layer, and it just forms one like that. And here, what is the analogy is just placing a polka dots on a dress materials on a certain pattern. For example, in case if you imagine on glue gun, a glue gun is glue gun is applied on a certain cloth. So what happens? That glue gun gum will be sediment on that particular dresses one by one layer. So after getting solidifications, so it will be make one by layer additions, and you can get some refined patterns. This is what the laser assisted printers is also working. And here the limitations is it works only in the very low printing speed, and here you cannot make the multiple print layers easily. So for one layers and for the next layer generation, you have to wait for a long minutes. So, but here it has the advantages of getting this entire layer by layer preparations with high accuracy. So that is the one of the advantages. And here the wasteness. So more number of biomaterials will go as a waste. So by using this particular 3D bioprinters, because it is by using some laser operations, some of the biomaterials will get dispersed or some even diffracted by use, and it may go for some wasteness. So this is what the limitations. And the best application is that the placing cells precisely into some solid structures. For example, nowadays in defense sectors, if a particular soldiers has been under some injuries or using some in wars or some bomb blast. So where in case if you want to place some living cells only on that wounded area, this types of particular printers has been mostly used nowadays. So several several countries like particularly UK and US, for their army purpose, for the defense sectors, they're using this laser assisted 3D bioprinters for making that army persons to make their wound injury, to get rid of their wound injury as early as possible using this 3D printing techniques. And this is what the laser assisted printer was working. And the next one is, sorry, actually in this slide there is a small mistake, not laser assisted printer, it is an extrusion based printer. So it is working under just as a squeezing SketchUp over a bottle. So the same techniques that is happened here. And here what are the limitations is that particular material, it should have some lower cellular viability. For example, here it works on three principles. One is by even in case if you apply certain pneumatic air on the other end of that cylinder, so that particular biomaterials or bio ink will squeeze under this nozzle. So it made the biomaterials to print one layer by layer. And the next one is by using some piston arrangements. So in case if your piston is arranged done like this, so here in case if you look at this, so here, sorry, once again. So here it is it is a cylinder and nozzle arrangements. So when a pneumatic air is applied over here, it just is squeezed through this entire nozzle. So it just squeezed through this entire nozzle, and it will be deposited layer by layer of biomaterials, and we could able to print, you could able to get some tissues or organs like that. And another one is by using this piston arrangements. In case if your piston is actuated by using either pneumatics or hydraulics or by using certain actuators, so here the biomaterials will squeeze over it due to this piston compressions, and the biomaterials will squeeze over this entire nozzles, and it will be deposited layer by layer. And the next and the last mechanism is screw mechanisms. Once if the screw has been actuated by using certain DC motors, so at the other side some inlet materials will be happened. So here some nutrients or another type of materials, biomaterials has been added one by one. And in case using this particular techniques, several nozzles can be implemented. One or more nozzles can be implemented using these types of screw extrusion techniques, where the extrusions of biomaterials will be on layer by layer. It is also possible for all these things that biomaterials should have low cellular viability, and it should be the low resolutions. And as usual, as like the laser assisted 3D printers, so here this extrusion based 3D bioprinters is also print only at the low speed. So mostly these types of printers are usually created for creating large 3-dimensional biostructures. So mostly in case if you want to develop some human livers, so where the area will be very long, so at that time they have to focus on these types of 3D printed extrusion based 3D printers. And in case inside that particular human livers, in case if there is a special detailing about the vascular areas, where you have to focus on some other printers, where it should be based on some or more methods. Okay, so now I have completed about all these types of bioprinters. Now I am going to show you one more video. In this video, that animations, that all these types of bioprinters has been explained with full animations. Now I request you all to watch these videos. The video is almost for 5 minutes. So at the end, we can discuss later.
Bioprinting, also just known as bioprinting, is a relatively new technology that, in theory, would allow humans to fabricate nearly any tissue or organ from scratch. The fundamental idea behind bioprinting is quite similar to that of ordinary 3D printing, in which a material, usually plastic, is printed, one layer at a time. Instead of plastic, however, bioprinters use bioink,
usually composed of cells suspended in a special gel known as a hydrogel, which helps to protect, nourish, and hold the cells together. Some bioinks use a single type of cells, while others contain multiple types of cells, or multiple bioinks are used side by side, each with a different cell type. There are three categories of bioprinting that I will be discussing in this video, which differentiate in the method by which they turn the bioink into a specific shape. Note that due to the fact that this is an emerging technology, the exact name and classification of various methods vary from source to source. The concepts, however, are universal. I choose to group the various bioprinting methods into the following categories: extrusion-based bioprinting, droplet-based bioprinting, and energy-based bioprinting. Extrusion-based bioprinting is similar to what most people would think of when they think of conventional 3D printers. It involves forcing continuous filaments of a material through a nozzle in a controlled manner to create a 3D structure. The material is bioink, which, as I said before, usually consists of cells and a hydrogel. The filaments are forced through a nozzle by either pneumatic pressure, which is basically air pressure, or mechanically derived pressure, which comes from things like pistons or screws. The bioink must be stabilized quickly, or else it will not retain its shape. The bioink can be stabilized in a number of ways, largely depending on the hydrogel that is being used. As an example, during printing, the bioink can be stabilized by spraying a mist with a cross-linking agent dissolved in it. By the way, cross-linking just means linking one polymer chain to another, and this is done to stabilize bioink. In contrast, droplet-based bioprinting deposits discrete volumes or droplets of bioink onto a surface. Droplet-based bioprinting methods include inkjet-based bioprinting, microvalve-based bioprinting, and laser-induced forward transfer bioprinting. As with extrusion-based bioprinting, the bioink must be quickly stabilized in order for the structure to retain its shape, and the exact manner in which this is accomplished depends on the hydrogel being used. Inkjet-based bioprinting shares a lot in common with traditional inkjet printing. Here's how it works. At a high level, a pulse of pressure is used to eject a droplet of bioink. The pulse of pressure can be generated in one of two ways, using thermal mechanisms or piezoelectric mechanisms. In the thermal mechanism, a small surface of the bioink is heated and vaporized to create a bubble, which occupies a larger space than the liquid bioink did, creating pressure, forcing a droplet of bioink out of the nozzle. Once the bubble collapses, a bit of bioink is sucked from the reservoir, refilling the chamber, and the process is repeated. In the piezoelectric mechanism, an electric current is applied to a piezoelectric actuator, causing the chamber to deform slightly, forcing a droplet of bioink out of the nozzle. By the way, a piezoelectric actuator is a device that responds to an electric current by stretching and bending. Then, when the electric current to the piezoelectric actuator ceases, the shape returns to normal, and a bit of bioink is sucked from the reservoir, refilling the chamber, and the process is repeated. Next, microvalve-based bioprinting involves small valves that can be accurately opened and closed with electromagnets to deposit droplets of bioink, which is under pressure, usually pneumatic pressure, meaning air pressure. Laser-induced forward transfer bioprinting uses lasers to accurately position cells on a substrate or the place where the tissue will lie. Laser-induced forward transfer bioprinting consists of a laser, a focus lens, a ribbon, and a substrate. The ribbon could contain a sheet of transparent quartz glass with a very thin gold coating and a coating of bioink. When the laser reaches the gold, it heats it and greatly expands it, propelling a very small amount of bioink to the substrate, which will have been coated with hydrogel to dampen the kinetic energy of the droplet of bioink. This laser is quite precise. and hence this method is also quite precise. Finally, in energy-based bioprinting, a focused energy source, often a laser, is used to selectively solidify or stabilize a bioink. This method differs from extrusion-based bioprinting and droplet-based bioprinting in that the bioink is already in place. Perhaps the most notable method of energy-based bioprinting is stereolithography. In stereolithography, a laser is employed to selectively harden a small amount of bioink, which contains a light-sensitive hydrogel. This substance lies on a platform that is then moved away from the laser by a small amount. If, in doing so, the platform is immersed into bioink, then a fresh coat of bioink will flow on top of the now hardened layer of bioink. Or, if the platform has sidewalls, then a fresh layer of bioink can be coated separately. This process is repeated, eventually leaving you with a solid 3D structure once the liquid bioink is washed away. Each category of bioprinting has its own pros and cons. I won't bore you with all the specifics. However, as an example, laser-induced forward transfer bioprinting is precise and has a high printing resolution. Nevertheless, it is expensive, cumbersome, and time-consuming. Hence, different methods are used for different needs. Interestingly, there are approaches being developed that combine different bioprinting methods in order to maximize efficiency. Maximizing efficiency is crucial for bioprinting certain structures like organs. In general, organs must be printed quite quickly, and yet they have certain parts that contain lots of details that consequently require bioprinting with a high resolution. Other parts don't need to be printed with such precision, and time can be saved by not printing at such a high resolution. So, by combining certain methods that print slowly with a high resolution with those that print quickly with a lower resolution, one can optimize the bioprinting process. While these bioprinting methods are based on 3D printing, living things develop and change over time. Hence, bioprinting can often be thought of as forward.
So, welcome back. So, hope you have known about some of the basic operations of 3D bioprinters and what are the types of bioprinters and how the bioprinters mechanisms works and what are the principles behind it and how there's hybrid types of bioprinters. For example, in case if the human heart has been it is a requirement to print the human heart where it is having high vascular structures and also certain vascular tissues is having high detailing. For that, for making some optimization things where they have combined one or two bioprinted methods. For example, one in case if a laser-assisted method has been utilized as one method, after that some extrusion-based 3D bioprinters is also used for certain things. So just to make the process in most fast and make the entire process to get a high efficiency manner, and also the quality in the quality aspects, it should be in a very good quality. That's why this entire optimization should be done by integrating one or two methods. That's what the bioprinters are doing. And next we have to discuss about some of the materials for bioprinting. So in case before going for discuss about the materials, let us discuss some of the important property which is required for a biomaterial. So the first and very foremost important property is printability. So whenever in case if you have taken any biomaterial, so it should have the capacity to build layer by layer adhesion. It should have certain adherence capacity, and that's why it could be able to it could be printable. So that's what it is, a printability, and certain mechanisms should be done by using those types of biomaterials, and that material should be degraded or else the tissue cannot be regenerated. And functional stability, so it is also one of the important property of a biomaterial. So all these four related to the properties, that is the important property of that biomaterials. And later on, let us discuss some important biological property. So in case if you have selected certain tissues, certain biomaterials or bioinks, especially for certain organs. For example, liver organs or kidneys or for lungs or scaffolds or some tissues or skins, etc. like that. It should have each and everything has unique biological property. So for that you have to verify it. So one is biocompatibility, whether in case if you have selected certain biomaterials, whether it is compatible for this particular organs, whether this particular material is compatible for this particular organs. Because for certain organs, it has the capability to take some blood circulations higher, and for certain organs, it has the necessity to take some oxygen supply. So for that, some biocompatibility is one of the important parameters where it particularly suits for this particular region or particular organs. Then cytocompatibility. And that cytocompatibility is also one of the important property which is required for a biomaterial. And bioactivity. So for example, in case if you are utilize this particular biomaterial for several long durations with certain temperature variations, whether this ability of this particular biomaterial, whether it is degraded or whether it is regenerated, that is also comes under the account. So therefore the bioactivity is also it should be looked into considerations. And here there are some material purposes that one is sacrificial in another materials that can be washed away after printing for temporary support for certain development, particularly vascular structure development. So for that, some sacrificial biomaterial should be needed. So it is one and only for the purpose of support material. And another one is matrix formations. So therefore that certain cell encapsulating materials is also there, that is provided with some structure and nutritions for certain cells. So for that some matrix needed materials is also there. And again some support materials, it should provide some permanent support for enhanced mechanical properties, for a building some layer by layer buildings with some certain chain mechanisms. So for that you need some support materials which should be biologically accepted. And for curing material process, that materials that cross-link matrix and reagents through photo curing or chemical processes. This is what the purpose of this curing materials. And so here in my presentations in the later slides, I have discussed about some of the important material. So I am not going to tell her these are the only materials. These are some of the important materials which is used generally for most of the bioprinting and also some organ printing. The first one is alginate. Alginate is nothing but it is one of the material which is extracted from the natural things, particularly from algae. So it is a polysaccharide which is derived from a natural algae. So easy iconic cross-linking is possible by using these types of alginate. And it is a widely biocompatible materials. So it can be biocompatible to all the humans, insects, and also for animals, etc. So this alginate is one of the important material which is used for bioprinting. And the next one is collagen. There are several types of collagen is there, type 1, type 2, and several types of collagen is there. So generally it is called collagen. It is one of the most abundant ECMs. So ECM is one of the coarse one side, one of the matrix formation, and it supports some cell attachment. And it is a temperature related temperature related dependent gelation. Okay, so it is one of the important biomaterial property which is used for most of the organ printing or bioprinting. And gelatin. So we already used this gelatin in most of the food processing. Likewise, for bioprinting also, this gelatin has been utilized. So it is mainly derived from denatured collagen, and it is also the temperature dependent gelation. And it can be chemically modified for photo cross-linking, that is GELMA. Okay, it is also one of the important biomaterial. And pluronic, it is one of the artificial biomaterial, that is, it is a synthetic copolymer. It is from an extract of one of the polymer materials, and it gels at room temperature. Mostly it is available in the gel format, and it is used as a sacrificial material. And the next important thing is cell-laden hydrogels. So most of the tissue generations and most of the tissue regeneration, vascular regenerations, this cell-laden hydrogels is being used. This bioink formulation utilize natural hydrogels like algase, alginate, and cytosine, collagen, gelatin, fibrin, and some of the hyaluronic acids, which is used to main the biolink formations for this cell-laden hydrogels. And some synthetic hydrogels is also available, where it comprises of some pluronic and some polyethylene glycol, that is PEG, and some blends of both these entire hydrogels. And this is what in the picture it represents about the formation of this entire cell-laden hydrogels. So from the natural extract, that is from the natural hydrogels, it can be converted to some sol gel transitions by using certain methodology. So here in this methodology, they used sonifications, or sometimes they have used UV sonifications or some other mechanical processing for making this entire component from one form to other, and they have blended some other extracts and they made some cell-laden solutions, and using this ultraviolet cross-linking, they formed at last these types of cell-laden hydrogels. This is the process for making the cell-laden hydrogels. And another one is decellularized extracellular matrix based solutions. So mostly it is a decellularization of a tissue of interest by removing the cells while preserving this ECM, and also it provides some novel opportunities to fabricate tissue specific constraints. So mostly some chemical decellularization is also there, some physical decellularization objects is also there. Based upon the certain methodologies and the solutions, so we can get this DCEM materials, which could be widely used for most of the tissue generations and some tumor treatments and some most of the biological aspects. This DCEM based solutions has been utilized. And now we can discuss about some of the basics of tissue engineering design process. So in the earlier slides, we have discussed about some of the important biomaterials. So now we could understand about how the tissue design process has been done. The very important, the first step is you have to identify the functions are being replaced. So first you have to know about at what tissues or what organs that we need to go for some replacements or some transplantations, etc. What is the first thing we have to go for it, and then we have to choose some cell determinations. In case if you have selected that particular function is infection mostly takes place in one particular area, that is take an examples of liver cells. So in case if you have identified the particular area for replacement or transplantations, then you have to determine at which cell which is particularly compatible for those particular organs or particular tissues or particular vascular cells. Once where we have to do some next level research, you have to determine what types of cells has been there and what are the types of cells, and then you have to go for some biomaterials. That biomaterial which is most capable for those particular types of cell types, that is the next step. Then there are having several types of biomaterials are there. So once this biomaterials has been identified, then you have to go for the construction method. That is absolutely you have to print those types of materials by using some 3D bioprinters, and you have to select at which bioprinter is most compatible and more optimized for printing these types of organs or printing these types of tissues, etc. For that you have to do. And at the last stage is construction of this entire three-dimension biomaterials, that is also some organs or tissues, etc. So this is what the tissue engineering deals with. Even in case all the scientists and doctors which is working under this tissue engineering has been followed these practices, and the major once if you are strong in this first 3 steps, then only you can enter into this bioprinting areas. And most of the areas that you can, the researchers and spend in identification of the cell types, identification of the biomaterials, and then the challenges of this engineers is to make the accuracy, the full accurate and the full compatible and the full complexity structure creation using these constraints. This is the challenges faced by the engineers, and moreover in that side the doctors or biologists then make the determination of the cell types and biomaterials, etc. like that. And at the same time the final constructions, there you can get some organs where you have to go for the further process like evaluation and testing, and based upon the results then we can to go for some other reports whether it is feasible for implementation or not. So this is what the final basic tissue engineering design process that is following nowadays. And there is one more challenges. So once in case if you are printing this particular component by using this bioprinters, that particular cells must survive during this printing. It should have certain oxygen supply, and it should have certain nutrition supply, and it should withstand the particular temperature, where it should also withstand some high temperature to low temperature. For all these aspects, it should fulfill their expert needs, or else that tissue cannot be regenerated and it could be gone for a scrap. And these are the applications of this particular bioprinted materials. So one of the main application almost in this STTP, most of the speakers as you focused mainly upon these applications. So that's why I made this application in a single slide. So one is tissue assembly. So most of the human tissues and animal tissues and some this one damaged tissues has been assembled using these types of bioprinting. And reconstructive surgeries. So most of the complicated surgeries where they have get practice by using these types of reconstructive surgeries, and absolutely some organ transplantation and organ, they have used these types of organ 3D printing. So where it is applicable, this bioprinting is applicable in organ transplantation also, and some stem cells regenerations. So it is also related to the tissue regenerations, but nowadays a stem cell regeneration process is also quite normal using this bioprinting process. And some testing drug discovery or drug mechanics is also possible using these types of 3D bioprinting processes. And microfluidics. So you all heard about the term fluidics, where fluidics is in case it is natural types of natural wall which is occurred in our human arm, even in case inhale and exhaust oxygen and carbon dioxide using our lungs vessels, etc. So likewise, so fluidics is microfluidics is one of the times where we can get some fluid supply, even like oxygens or blood circulations and nutrition supply, where at one time one particular nutrition will travel through this particular vascular tissues, and for some other times another types of nutrition should carry out by this particular vascular tissues. For this, microfluidics arrangement is possible. So when the microfluidics along with organs which is integrated, then it could be possible to form an organ on a chip. So organ on a chip means, so even our human organs can be blended or integrated with some microfluidic devices, which is a very quiet, which is a micro level or nano level components, which is also possible by using this 3D bioprinting. And human on a chip is also the same, which is integrated along with microfluidics with some electronics actuators. That's why it is known as human on a chip. And the last thing is animal-free meat. It is mostly used in the food processing industries. Now, in case if we need some non-vegetarian meat or beef or mutton, chicken, etc., we need to kill certain animals. But using these types of tissue regenerations and bioprinting, we could able to get chicken or fish or meat, etc., by using these types of 3D bioprinters. So that's what animal-free meat is also possible, which could be a quite new emerging areas for the food processing industries. And these are the most common applications which is quite available using these types of 3D bioprinting materials. And now I am going to focus about one and only the operation challenges. So absolutely, the high level customization is required, which is using while using these types of biomaterials and bioprintings. So where you already know the structures complexity of that human heart, the structure complexity of the human livers is also very quite complex. That's why still most of the engineers are facing high level challenges for making these types of customization, because for particular area where it has certain vascular tissues where it needs a high where it needs a high detailing or high accuracy, and for certain areas it is only having some fleshes or muscles where it is having less accuracy. So high level customization is required. This is one of the operation challenges in this area. And the next one is integrating these living cells or tissues to make the requisite of the complex structures. Even the producing this plastic parts is easy by using these types of 3D printing, but while integrating these types of living cells along with these types of bioprinting components, it is quite complex. That's why it's still most of the organs that is printed using these techniques is still in the research level. And the next one is opting it as a business model is very, very critical, because it is, while in case if you go for certain business model, absolutely revenue generation is very, very important and price fixing is important. And while it is a highly customized object, where the pricing and the revenue generation is not quite normal for all types of organs. So it varies from persons to persons. Biomaterials, for one person the biomaterials will be compatible, and for another person some other biomaterials may be compatible. So this revenue or pricing will be the major challenges for making it as a business model. And the demand and the supply chains is also quite complex issues for making it as into a business model for making these types of organ printing areas. And the next one is the trust of adoption. So absolutely, even in case if one patient has got some failures in their own particular organ, they are definitely seeking for one particular donors. So even in case if a mechanized donor, that is if a 3D printer is the only donor for in our cases, so where the trust of adoption is quite complex, even people like us don't easily trust this particular type of 3D printed organs easily, because where they need high number of research trials has been needed, and several researchers and several research reports which is needed for make this type of trust of adoption among the customers and among the public. So that's why this particular research area will need several more years to make it into the successful commercial aspects. And the customer perceptions on quality aspects, even in case even any customer, in case if they purchase normal safety pins, they expected the quality. Likewise, in case if they purchase or certain 3D printed organs, definitely they expect more high quality. So proper validation and testings reports that will be done not only for a single patient, several patients and several animals, that reports that be needed, and making into some making the summary of this collection of reports for certain years, then only it made that entire things in a good quality aspects. And there are some material challenges in this bioprinting areas. One is chemical compositions and importance of bioink. So all bioinks cannot be in the same compositions. For each and every tissues and liver cells, some in specific chemical compositions has been required, and certain flexibility in tissues and organ generations. So the tissue regeneration is quite complex for certain particular organs, and for certain organs it is quite easy. So it should be flexible to all types of organs. And absolutely the bioinks, that availability of that bioinks is still under the major question. And the nutrition supply. So for certain bioinks or certain biomaterials, the nutrition supply is quite easy. For certain things, it is quite complex. So this is also one of the major challenges of the selection of these biomaterials. And the bioinks or biomaterials for the unique organs, it is also the quite complex. So nowadays the materials, that unique organ, say it as an example of an heart, the bioink which is required for the heart generation tissues is very, very complex when compared to the human livers. So that's why these are some of the material challenges that has happened in this particular area. And that's all. And the last here, I have presented some of the case studies. So these are all the researchers has been successfully implemented in their research work. So I have taken it from the recent journals. So one is Zhang et al. And his team. By 2019, they have successfully made the bioprinted thrombosis by using this on-a-chip methods. So here they used microfluidics methodologies. So in this thrombus, they have successfully implemented, and they have the testing reports they have supplemented, and they have published in one journals where it is quite successful. And the next one is Ko et al. In the year of 2019, they have successfully implemented a tumor-on-chip system with a bioprinted blood and a lymphatic vessels pair. So here it is the entire diagram of their functional model. So where they are used for the tumor treatments. So they have successfully implemented, and the results of their entire research has been made a successful one, which is useful for some other researchers. And Lee et al. And his team in the year of 2019 has successfully completed the 3D bioprinting of collagen to rebuild the components of the human heart. Because nowadays still the printing of the entire human heart still is $1 million challenges. So for that, they have successfully made this particular human heart collagens to rebuild the components. It is made, the results has been satisfied. And sorry, it is Riva University in USA has successfully developed this artificial air sac. So here, in case it is an air sac which is developed by Riva University, it's not Rice University, it is Riva University. So where the blood streams, these are all the blood streams where the blood passes from one place to another places has been successfully implemented in one model. I think that they have implemented it to one particular animal, and they have tested it, and still it is a successful one. And the last, now I am going to show you one small video. So here one of the researchers in the European countries has been successfully creating some vessels for the particular heart. So wait. So just made it as it is a 4 minutes video. After that I will close my presentation.
From layers can be used to make many different things. Printing one layer at a time, 3D printers use materials like plastics and metals to build intricate and complex objects, such as tools, replacement parts, even prosthetics. In engineering, this type of construction is referred to as additive manufacturing. In Pittsburgh, one biomedical engineer has even invented a way to 3D print human tissue, an innovation that could one day allow us to print a working human heart.
The actual human heart is incredibly complex, and we don't necessarily need to mimic every feature in there. What we're trying to create is a minimum feature set that really recreates the core properties of heart muscle tissue.
Adam Feinberg, a professor at Carnegie Mellon University, received a 2015 Career Award from the National Science Foundation for his work on 3D bioprinting. His research touches upon a crucial aspect of innovation: how scientists and engineers improve upon the work of others to make things better, faster, and cheaper. Feinberg didn't dream up the idea of 3D printing, but he's improving and adapting the technology to solve big needs.
We really pull understanding, knowledge, technologies from anywhere we need them and combine them to solve what we need to solve. And I think out of that process comes innovation.
The problem Feinberg hopes to solve is a method for bioprinting human heart tissue and growing it outside of the body, an achievement that could help millions of people who suffer from heart disease, an affliction that kills more than 600,000 people in the United States every year.
Heart disease is the #1 cause of death worldwide, and really the problem is that the heart doesn't regenerate. If your heart becomes damaged, the heart muscle cells inside just cannot divide and regrow that damage. So once the damage occurs through a heart attack or a lot of other diseases, it's permanent.
Since the 1960s, artificial hearts have helped patients live longer. However, artificial hearts can cause blood to clot and are still a continuing problem. Heart transplants offer another option for patients, but there are a limited number of hearts available for donation every year. Feinberg thought he might be able to bioprint new heart muscle tissue using 3D printers. But first, he had to figure out how to get them to print soft tissue-like material.
Soft materials deform under their own weight and air. So when you go to 3D print that, you're going to lay down one layer. If you come down and put the next layer on top, that first layer will now move. If that first layer moves, you can't put the second layer on top.
After a lot of trial and error, Feinberg invented a process that prints a soft gel inside a second support gel. This allowed him to print delicate, soft structures that could support heart muscle tissue without it collapsing onto itself.
The support is really what we 3D print into. It's made out of a gelatin slurry, which is really just these very tiny particles of gelatin. You can think of them like grains of sand.
In this demo, Feinberg starts with a 3D image of the coronary artery, a major artery which supplies critical blood flow to the heart. Instead of printing with actual heart tissue, he uses alginate, a polymer material derived from algae, which he prints into the support gel. After the artery is printed, the support gel is melted, leaving an exact replica of the artery. This replica acts as a scaffold to grow human heart cells, like the scaffolding that surrounds a building while it's being built.
You can either actually print cells in the scaffold during this process, or you can basically coat the scaffold cells afterwards.
While we're still many years away from bioprinting a full human heart, Feinberg says that within 5 years, we may be able to print heart tissue, a breakthrough that could allow researchers to test drugs on 3D printed heart tissue instead of through costly human trials.
We can make human heart muscle in the dish that you can test these drugs on, and the human heart muscle basically has all the unique properties of the actual human heart.
Feinberg has 7 patents issued by the U.S. Patent and Trademark.
So this is one of the researchers where they have successfully created the heart tissues, and which is implemented in that one of the patients, and it is still in a successful research report. And these are the references that I have made so far for making this entire presentations. Now, thanks for the opportunity given, and once again I thank Atal and AACT for making me to present this 3D bioprinting and organs related things, and also some of the biomaterials in front of you. And now it's the time for question sessions. In case if you are having any queries, you can ask. So thank you. So thank you, sir. Shankar sir.